Hi everyone, thanks for joining our webinar today. We're excited to share the latest on 3D printing and when you should take additive manufacturing to production. First, I'd like to introduce myself. I'm Shilpa and I'm on the marketing team at Xometry. A couple quick notes before we get started. Please submit questions throughout the webinar for our presenters to answer at the end. I'll be monitoring the question box on the GoToWebinar panel, so submit them at any time. And remember, it's chat-based questions. We'll also send a webinar recording around for anyone who'd like a copy and free to share with your colleagues at the end. Next, I want to introduce our team. First, meet Greg Paulson, Director of Applications Engineering at Xometry. Greg brings many years of experience in leadership to our team here at Domtree. He's an expert panelist and speaker on all things additive manufacturing. He's also the star of our Engineering Challenge YouTube video series. Before Xometry, he actually was a project engineer for many years doing rapid prototyping. So he brings subject matter expertise as well as manufacturability expertise. Next, I'd like to introduce Tommy Lynch. Tommy brings over a decade of experience in additive manufacturing with hands-on experience in 3D printing, with direct experience in SLA, SLS, DMLS, FDM, and urethane casting. For Xometry, he is the head application engineer for anything additive. Tommy would be your go-to for any special requests when it comes to materials, processes, finishes, and production requirements. So thanks again for tuning in. Don't forget to submit your questions on the webinar chat. And with that, I'll pass it over to Greg.
All right, thank you so much again, Shilpa, and thank you all for attending today's webinar. We're really excited. I know both Tommy and I, we love talking about making parts. So, this is our passion. This is what we do here. So, to kind of talk about, we've talked about our team. The agenda for today is I want to go briefly over what's new on Xometry and where we're going. As well as bring up a recent case study we did on scaling parts from production, some considerations, and that'll segue into Tommy talking about 3D printing for production. So the guidelines that we're talking about, the advantages and trade-offs that we have, and then we'll be closing up for just some resources that we have, as well as a live question and answer session. As Shilpa said, Q&A, I think, is some of the most fun things that we do here with these webinars. So if you do have any questions as we go along, please make sure to use the question section on GoToWebinar, submit those, and we'll be addressing them at the end of the webinar here. So let's talk about what's new on Xometry. A lot has been changing recently. We've been adding more and more materials and processes, and our goal is to be that comprehensive resource for you on actually building your projects and making your projects a success here. So the website, if you guys are not familiar with our website, is full of resources that we are continually updating. And if you go to our resources page here, you can check out our design guides. I recommend going to our production guide here, which is actually kind of a 2-pager per process that we offer, showing you some of the strengths, trade-offs, and giving you an overview, especially if you're in that help me choose environment. This is a really good place to start. And of course, we have our more in-depth design guides for CNC machining, sheet metal fabrication, DMLS, direct metal sintering, and so forth and so on. And as we add more and more processes like injection molding, for instance, you're going to see more and more content built around this. And these guides are built by us because we have experience making parts. So we hope that they are effective tools for you for your next design project. The other thing, of course, is our comprehensive FAQ, which is literally when you press search, we see that data. You can search also in your chat tab that's in the lower left of the screen here, get some questions answered very, very quickly, and you can use this resource and build up. And as we look at these resources, what's cool is we're able to see what you're searching for, and if we don't see something that's there, we're either going to add that content to the design guide or build a new article around it. So here I'm just showing off a very cool surface finish gallery. So if you're like, what does my part look like, or what will it look like when I order it, this is a really great place to get started. And of course, everything is focused around our instant quoting site. We use that 3D, we use a 3D CAD model, and we actually use computational geometry to price that out in many, many processes all at once. And I'll show you very briefly here because I want to get to talking about production. But this is how powerful our website is. The second that you upload, you guys may have missed that, but the second that I uploaded, I had a price and lead time right away via our website. I can go and look through different materials over different manufacturing processes. So from CNC to sheet metal to casting to 3D printing, I can select what process that I'm looking for. So let's make this part out of glass filled nylon, for instance. And then I can actually add, this part, let's put 4 tapped holes in it and start building your part for spec manufacturing, whether it's in the additive or subtractive process like CNC machining. So just as easily going through again, for CNC machining, let's take this part, let's turn it into a machine piece. Let's give it, it still has its thread and tapped holes for it. Let's black anodize it. And heck, let's make 156 of these. And that's how quickly our quoting site works and how powerful it is for a tool for essentially getting the job quoted and being able to place an order and get that job in process right away. We're really trying to hit that supply chain need. On the website, you may have also noticed some increased features when it comes to part marking, as well as inspection requirements for certain processes. We've recently added those, and if you guys were part of our last webinar, you may have seen me talk about these in further detail. But now if you do have, for example, a requirement to add a standard inspection where you receive a dimensional report, it's as easy as applying it directly to your part, and there you go. We also are constantly working on certifications and other requirements as we move up to spec manufacturing. So if I need to add a CFC, or this is an ITAR part, which is a defense restricted part. Again, just one click away. So I want to show you this because I want to show you like how powerful this tool is and how amazing it is to see all these processes all at once and being able to preview the price and kind of understand lead time consequences as you're working through your project. Because sometimes you may be in a situation where, depending on your time or your scope of or the budget that you have, or how much inventory you want to have on hand, really, you may be choosing a different process to fit that need. And again, with Xometry's tool, it's very easy to go from one process to the other and kind of weigh your odds and see what works best given your timeline requirements. In this case, I have quantity 15 of this piece black anodized, but maybe I just need a piece that actually is black and a plastic can do. I could actually build this in, for example, FDM plastic quantity 15 for cheaper than I could with with CNC machining, and about 15 days sooner. So this is a really powerful way to compare and kind of show you what that looks like across multiple processes, and kind of how to help understand how you can use Xometry's web service as a tool for you on making these decisions. I've actually gone through and I created a recent case study on 3 parts and how they look like and what they look like via Xometry's quoting over multiple processes. And what you're looking at here is essentially your quantity up top. So quantity, I just kept on doubling up to 1,024. And the per unit price. So this would be the total price divided by that quantity. And what's really exciting about this is you can see how certain geometries can affect which process is most optimized for manufacture as far as cost effectiveness goes. And I have a bulky piece, which is this 5-inch quarter cube. I have a smaller piece, a little 1-inch piece, and I have something that kind of I use. It's a walkie-talkie piece, but I use it to represent what you would, like, kind of what I consider a Internet of Thing or an electromechanical assembly piece, because it's very, very common to see, especially when you're making a decision of should I go to mold tooling or should I use additive manufacturing for that. So in this case, I have a big bulky piece here. So yeah, it can be cost effective with additive, but there's certain constraints that Tommy will be talking about with the things that take up a lot of space. So you find that traditional methods may win out here. So CNC machining and eventually injection molding tends to be more competitive. Even things like cast urethane kind of have a sweet spot somewhere in that 10 to 30 range, looking at the cost trade-off. But as you move to different geometries, so for example, this 1-inch spacer, you can see how different additive processes just really can shine in that area. So in this case, SLS can take pretty small pieces. It could actually build in mass very, very easily. You just stack these parts up in this machine, so you tend to get a very good economy of scale on these pieces. And you can see here that although it asymptotes really quickly at about that $10 mark, it is so cost competitive that you don't really see anything catching up until injection molding well past 200 pieces. And again, it's something to understand is, yeah, these are different manufacturing processes that are just something else that you get access on the shop floor. And what's really required is just that understanding of what results you're going to get, and really what your ultimate goal is, and who's going to be handling this product, and what material performance is required. But I thought this was a really compelling example showing like how, hey, if this is a spacer, I really need to get that geometry, get that unique performance, and this is something that SLS can perform very, very well. And maybe eventually I move to mold if I start looking at the thousands or tens of thousands of units. And the third part of our case study, and I recommend going on Xometry's blog and checking this out for further detail, was this handheld radio piece. So a lot more complexity. So it's not something I would traditionally CNC mill. When you're making these considerations, what's interesting about this is, yeah, I can make this out of 3D SLS, but this may be something that I want a little bit more of a cosmetic finish for. And you can start to see kind of a sweet spot on cast urethane, which is a surrogate of additive, to where it starts to hit right around that 50 range or so as something that can be really useful. But even on the SLS side, I can usually media tumble or die or hit something that bridges that gap. But again, notice that each one of these, the ramps are a little bit different, because what we're looking at is that 3D file. Really, what is the product that you're giving me? Because it is very basically build dependencies are determined by geometry when it comes to additive, as well as setup times and machining required is also always determined by that part geometry, which is why everything in Xometry starts with that 3D CAD file. So I want to pass this over to Tommy to kind of talk about 3D printing and production, and what you need to consider when you're thinking about, hey, I'm working on this new project, or I have a current project in process, or a vision change, or something else is happening. Should I consider 3D printing for this manufacturing, or for this next manufacturing round? So Tommy, without further ado, here you go.
Thanks, Greg. Yeah, glad to be here, and glad to be speaking with everyone. I do this day in and day out, and I still love it. So, over the past 10 years, well, actually more than 10 years, it's been really interesting, because when I first started, 3D printing wasn't even a word. But, over time, it's evolved from being kind of that mystery technology to where now I see corporate initiatives pushing for folks to have 3D printers sitting in their offices everywhere. So naturally, it's definitely evolved as a production method, and people are learning more and more on how to effectively use the different technologies. Just a few benefits of what I see in terms of using 3D printing for production is, in industries that are rapidly emerging, let's say autonomous car makers, they're building 25 plus cars at a time, and they need real parts, but they know that the designs are going to change after their first 25 builds. So they aren't really justified in investing in the tooling for injection molding at this point. So we have to provide strong, reliable parts that can ultimately be for end use applications. So number one, this allows folks like that to have design flexibility, even when they're going to higher quantities. When you're building parts batches at the time, then it's not a major effort to modify your CAD model and tweak a few dimensions here and there, and then start with the next round, and at very minimal cost for any sort of change. Number two is reducing inventory so that you don't have to order 10,000 parts at a time and have them clogging up your warehouse space. You can basically take the just-in-time approach, and as you need them, just hit the reorder button, and they're sitting at your door within a few days, or in cases of large orders, maybe a couple of weeks. But that's still, a whole lot better than what you may have experienced with traditional manufacturing methods. And then, number three, I kind of touched on that. I mean, we have technologies that realistically we can print and ship parts in as soon as 3 business days. So moving on to the next slide, I think it's worth touching on. Everybody knows how to use 3D printing for rapid prototyping, but what does that transition into a production model look like? And it will, it'll have a slightly different spin for each type of technology, and we're going to cover those in a little more detail as we get a little further on in the webinar. So just a few fundamental rules is going to be covered on our next slide.
And Tommy, just a note here, what's kind of beautiful, and actually you're in front of me here, is that you are working with the material in which you're doing your one-off and moving up to production. You're already understanding that material and process, which is very different from that prototype to moving to a different method. And right. A lot of people have adopted that really well.
Yes. You're definitely seeing an apples to apples comparison of how your prototype performs versus how the end use part will perform. But the main thing when moving towards the production model is just being sure that we're moving towards the most reliable, repeatable process that 3D printing can offer. And so what you want to do first, I would say in basically all cases or any technology, is I definitely deal with a lot of requests where folks will come in and be like, hey, I need 100 copies of this, and I need it fast so we can start installing it on our pieces of hardware. And but the parts have never been 3D printed before. So I strongly recommend to always start out with a few copies of the initial part. If you're looking for quantity 100, you might want to start between 1 and 5. And the good thing is you're going to just have those in a couple of days. And ultimately, you've got your insurance policy making sure that your larger investment for the higher quantity parts isn't going to be a waste of money, in the event that it doesn't work. So this allows you to basically hone your design before investing in the larger quantities as well. You have the option to plug this part directly into the application, see how everything fits, see how it works. And, as engineers know, sometimes there's a little bit of a difference in what shows up in SolidWorks versus what is sitting in your hand once you receive the parts. So it's always good to just do the measure twice and cut once approach, where, well, I guess in this case it'd be cut twice, but build your prototype, test it out, and then reorder the larger quantity based on the first attempt. And ultimately, this is going to minimize any chances for rework, because it's another common scenario where someone may see that they didn't properly size a hole for the right sized helicoils or something along those lines. And so now they're having to either go in and completely drill everything out, or they potentially oversized it, and now they've got to really get creative to figure out how to make those holes smaller. So again, prototype first, always. You're going to be in it for a couple of days, but it's a lot better than the alternative. So then on to the next slide. You know, once you have those parts in hand, I mean, you know, I was pretty much talking about this. You know, you need to verify your form, fit, and function, and you know, take all the measurements and just make sure that it's going to exactly meet your needs. That's the beauty of 3D printing. You've got the apples to apples, where you have your prototype that's directly going to translate into your production part. And then for the final steps, that's where you want to lock it in. At Xometry, we make it really easy to duplicate past success. For us, all you really need to do is, if you came in for some prototype parts and they worked out perfectly, then you just basically copy your previous order and specify that we need to build these parts the exact same as they were built on this, you know, quote, previous other order ID. Once you do that, that triggers, you know, a little bit of research on our side, where we have very quick visibility into how the parts were built, what machines they were run on, you know, exactly what the build orientations were, and it's very easy for us to duplicate success as long as we know ahead of time that that's what we're trying to do. You know, another thing that is always best practice is to create drawings for additive manufacturing, and especially things like direct metal laser sintering. I see a lot of customers moving towards specifying the build orientation, because ultimately this is going to affect your overall part resolution, and it will also affect the mechanical properties in some cases. Obviously, you know, specify the material on the drawing. You know, if it's FDM and you like ABS M30 blue, specify exactly you know, what you built last time, and then there's no questions as to exactly what's going to be needed down the line. And then the big one is, if you did during your form, fit, and function phase identify areas where you just absolutely have critical tolerances, definitely point those out. But you will want to be sure that it's appropriate for the technology. I say that because when we look at different printing technology, you know, direct metal laser sintering is going to have a different tolerance band than you might see from SLS. In general, I'd say it's safe to say that most things 3D printed are going to be starting out at a plus or minus 5,000 tolerance for, you know, any specific features, but then you typically tack on an additional thou or two per inch in length to any other features. So, you know, those tolerances can spread a little bit as the part gets larger. But yeah, you know, this identifies what we need to inspect to, just so that we can be doing exactly, you know, meeting your expectations and following what your inspection is going to be.
Yeah, and Tommy, just adding on to that, again, when we talk about traceability with digital supply chain, like what Xometry has, we know to the tool path on the part how we're going to do this. So, you know, on FDM, for example, if what we made is exactly what you want to get, down to the zig and zag on each layer, we can replicate that because we can use the same build file. And the same thing with digital traceability for other powder bed processes, where we could see the locations, the angles, and the settings of those builds, so we can actually replicate that. So it's referencing that previous order ID. It's really, really powerful when we move from that prototype to production phase. So we can make sure you're truly doing apples to apples.
Yep. Okay. So Yeah, as far as 3D printing options, you know, as I kind of touched on before, it's a rapidly evolving industry, and especially over the past couple of years. I mean, there's just so many different platforms and technologies and different methods of printing that are emerging and currently in development specifically for production purposes. You know, we've constantly got our finger on the pulse of the industry, you know, just to keep an eye out for you know, what's going to make the best sense for our customers. So what I'm going to cover here is our 3 core 3D printing technologies that we found to be very reliable for these production purposes. You know, number 1 is direct metal laser sintering. It has several different trade names depending on the equipment manufacturer, but you know, DMLS, SLM, DMLM, laser fusing. But you can see here, it's just basically you start out with powdered material. It has a solid build plate down under the bed of powder that the parts are being welded to. And then typically you're stacking a series of micro welds on top of each other that are going to be about 30 microns thick up until the part's complete. And you can see in between each layer, it just deposits another layer of raw powder, and until you end up with a complete part. So the strengths of DMLS are that you know, it's built with purpose. These are real metal parts. You know, a common question is, oh, what kind of fillers do you use? Well, with direct metal laser sintering, I mean, when we say it's made from 316L, it is made from real pure 316L powder, and that's it. And then, you know, as far as the benefit, you know, the comparison to the raw materials, you know, I typically tell folks that DMLS can be expected to exceed as cast properties, but not quite meet forged properties. So, you know, it has a lot of benefits in terms of eliminating tooling needs, and I've seen a few applications here recently where people are using like 3D printed aluminum as a stand-in for metal casting. It's allowing them to iterate on their designs, you know, over the course of having parts in 1 to 2 weeks, as opposed to waiting 8 to 12 weeks for a traditional foundry to make their patterns and pour their parts. So the final benefit is that, you know, for the most part, as long as you're following design rules, which we have design guides as well, complexity is free on well-designed parts. So you can really tailor this technology and use it to meet your exact needs. And it's definitely been well received. You know, as far as the considerations when looking at DMLS, you know, one of the limitations is that since it is printed out of a powder bed, it does have somewhat of a rough surface finish. The other thing is that it is orientation and platform dependent. So, you know, ultimately when people are designing their parts with an eye for DMLS production in mind, they're designing specifically for the process. And again, that is a whole nother webinar as far as, you know, the rules that you would want to observe or basically the best practices. But, you know, I guess the biggest thing that I see with DMLS is the tendency to potentially warp. And that's just because since you are taking metal powder from room temperature to instantly molten to rapidly cooling, every layer that stacks on top of each other just wants to pull upward. So we have build supports to help minimize that to some extent, but you know, it's definitely one of those processes where you want to prototype first, before you really move into production. But the good thing is once you get all of the components such as build orientation, support strategy, and all that locked in, it is a highly repeatable process. And then finally is the post-processing woes. You know, the first thing folks try to do when they see what the surface roughness is going to be is say, oh, well, you know, let's throw this into a CNC machine and see if we can smooth out the critical surfaces. Well, you know, that works in many cases, but it has to be a very thoughtful approach to get to that point. Because keep in mind, in order to get it to the point where it's going to be a successful machining operation, you know, number one, it has to be able to be fixtured or clamped into a mill, and then you have to have enough. I guess we'll say you have to be a little bit forgiving with your design, just knowing that there could potentially be some movement during build, and you know, the finished part may not be completely to spec.
Yeah, and I could talk to, I mean, these two parts here. So this part with the checkbox, this feature here is actually a way to hold the part so that our customer could post-process these fins. So this is actually not part of the final part, but this stem is literally just a way to hold it. So sometimes if you're looking for post-processing, that really needs to be a design effort up front. So begin with the end in mind when it comes to DMLS. And to exactly what Tommy was saying about things tend to kind of move and flex. And so if you have this, you know, perfect drawing with, you know, one central datum and everything's referenced off that datum, it may not be how that part actually will turn out in DMLS. So in this case, these holes were made via fifth axis machining with per the drawing via central datum, but essentially each one of these protrusions had just slight deflection. And when you go across the entire part, you could see, you know, very, very large differences in centering. So for example, if I'm making a drawing for a part like this, I will actually be, instead of calling out per like a central datum, I'll probably actually be calling out per center of each cylinder. So basically, in a machine, I would be using something like a Renishaw probe, for example, to detect the center and then drilling from there. Because internally, everything's kind of contorting the same with the part. But if you just would superficially, like on this part, like on this example, you may get, you know, you may scrap your part by accident. And that's something, again, you know, Tommy and I, we've had some experience on a lot of successes and also seeing some of these things. So we're always happy to help consult on what are appropriate next steps when you're designing for DMLS, especially with production in mind.
Yep. Thanks, Greg. So, you know, the next technology is selective laser sintering. I'd say the most I've seen this is you know, there are some consumer products that this is used in, but also it seems to be fairly popular within aerospace. The good thing about this technology is that it's, I mean, as far as any 3D printing that we offer, this is probably going to be the lowest price, especially you know, on parts that we'll say fit within a 5-inch by 5-inch, 5 by 5 by 5 cube. But ultimately, you know, this is we have two options that we offer: nylon 12 and then also a glass filled nylon. You know, this is just a good workhorse. You know, we have some additional. Well, actually, before we move on that, the video that we were looking at, you know, basically this is a powder-based technology, and as you can see, there's a roller that goes by. It deposits layers at 4,000 7-inch thick, and this whole powder cake is basically heated almost to the melting point, and then a laser shoots in from the top and images each 2D cross section. So moving on to the next slide, Strengths of this technology is there's no support structures that are required for build. Since the parts are encased in powder throughout the whole build process, it just basically supports itself. This is definitely different from the direct metal laser sintering and technologies such as SLA. So yeah, you've got a lot of flexibility with the design. The material being nylon 12, I mean, it's just overall a good general purpose, versatile material. And then beyond that, it's scalable. As you start packing more parts into a build platform, you'll see efficiencies when it comes to cost and lead time. So the considerations are that you are somewhat limited on the material options. As far as everything that's commercially available, it's going to be typically just some flavor of nylon 11 or nylon 12. Also, you only get one color. We can work around this by dyeing parts. I think we've got 6 different colors that we auto quote on our website. That's a really nice way to kind of brighten the parts, but just keep in mind that the dye doesn't fully penetrate into the part. It's only on, we'll say, the outer 0.5 millimeter skin. So if they're going to be taking a lot of abuse, then you might start seeing some white showing through as the parts wear. Surface roughness, since it is printed out of a powder bed, I like to say that these parts can be compared to a slightly improved sugar cube. And then also there's a potential to warp. I'd say that this is exaggerated on larger parts. That our standard durable white nylon build footprint is going to be about 13 inches square. So I'd say as you start getting towards the outer edges of that build footprint, then we might need to start looking at a different technology, just because as that whole powder cake is cooling after build, it cools from the outside in, and there may be some movement on the parts as they go through those thermal changes. And then also large thin parts, that can be the Achilles heel of SLS as well. Good thing is, if you want to try, you can probably try it out for less than $100 in most cases. So it's a good affordable technology, and then we're limited on what we can do for post-processing. Same deal with DMLS, kind of what you see is what you get, and if we have to start deviating from that, then cost shoots up quickly. And FDM, fused deposition modeling. This is a great technology. It's basically uses a print head that has filament running through it, and it just stacks layers of filament on top of each other. You can kind of see that in the image here, and if we can move on to the next slide, you can see some definite strengths. This is, hands down, our largest build platform at a footprint of 36 inches by 24 inches. It's really, really good for larger parts. We only run Fortis equipment, so that's kind of the industry gold standard. I know there's a lot of marketplaces emerging where you can get very low cost FDM parts, but in many cases, these could be just consumer grade printers or guys that are basically running printers in their basement, and they just haven't really been proven with the test of time. I mean, the Fortis equipment has been around as long as I've been in the industry, and this is definitely the go-to for all the major corporations. Benefits, you're going to have a higher variety of different types of thermoplastics, polycarbonate, ultim, ABS, and then multiple color options within those different types. And The other thing is high accessibility. Since these machines have been around for so long, there is, whether we're running these parts on our equipment or utilizing our partner network, we almost have infinite capacity for anything that needs to be printed in FDM. So as far as things to watch out for is small details. Since we are printing with filament and our standard layer thicknesses are going to be 10 thousandths to 13 thousandths thick, stair stepping is going to be very pronounced on parts with curved surfaces or slight slopes. So you need to keep that in mind. When it gets down to resolving holes and small features and thin walls, you will you just don't want to do this for high resolution printing. We'll leave it at that, and if you send over a part file, we're happy to point out the areas of concern. And then finally, the limited scalability on larger parts. Basically, there's not going to be any price efficiency gained when we're having to build one part per build. That's just kind of what the build time is, what it is, and we have to charge accordingly.
Hey, Tommy, thank you so much. I mean, these technologies, again, what we like about them is that they are consistent and they're repeatable. So these three that we highlighted today are ones where we typically see when we're going from beyond rapid prototyping to end use production parts. These are really the technologies that we tend to focus on. And just recap again, like when I'm looking at metal 3D printing, a lot of times I'm looking for something that is purpose design. Like I'm utilizing the strength of 3D printing to make my metal part. So if you have like a bulky part or something that would typically be CNC machine, it actually probably is not an efficient part to transfer directly over to metal printing. But it is something that if you optimize that, as if you made even wall thicknesses, kind of almost like if you're designing for metal injection mold or die casting, then all of a sudden you're speaking our language here for turning that into a production part. As Tommy mentioned, cast surrogates is super common here, as well as parts where you build like an all-in-one assembly, so multiple angles of fixturing. I've seen a lot of laser bracketings that actually come out through DMLS on a end-use side. But we see, lightweighting, we see medical pieces, parts for tooling that are coming out of this. I like to use different rules for what I see as a production side. And in this case, like metal 3D printing, like again, about the size of your thumb or a little bit larger. Usually, you can stack a bunch of parts onto a platform and get a better economy of scale. Or you work on that high value custom part where you're maybe looking at something that's anywhere between 4 to 9 inches, tends to work really well for DMLS. On the plastic, of course, we get like every technology here, we have the one-offs. When I'm looking at something that's as Tommy said, about 5-inch cube or smaller, I can move that to production. Xometry has that capacity. We're able to build many parts and essentially take advantage of that economy of scale, as well as parallel machines. So we don't just have capacity in a machine, but we have lots of machines to run in parallel, which is very important to say. It's something that's just telling about the size and the scalability that Xometry has. Benefit for this too is if you know that your design revision may change, or say for example you have like an Internet of Things device, and you have a bracket on the inside for your PCB. Oftentimes that hardware updates way faster than the tool life, and you may want to consider 3D printing because your design revision for 3D printing is I just changed the file. The machine doesn't care; it just keeps on making. But if you're working on a harder tool design or anything that requires setups like CNC machining, you're starting from scratch and building through. But yeah, if I have parts well designed for traditional processes, and I have this high level production, we're talking depending if it's chunkier part in the hundreds, or if it's a If it's, you know, a whiskier part in the thousands, yeah, let's look at CNC machining, let's look at injection molding. You know, we're not crazy here. Like, we understand the limitations of our technology, but I can tell you that we have very successfully worked with customers who have just turned these core technologies that Tommy went over into their end use production requirements. So this is what their drawing says. It will be SLS nylon 12 dye black. And moving forward, and we even gone the opposite direction of taking some parts, for example, that have been CNC machined in the past and moving them into a 3D printing technology to hit their just-in-time qualifications for their company. I'm mentioning this briefly, but again, it's a whole other webinar. Urethane casting, it's a bridge tool that uses 3D printed parts as a master pattern, and then you can make a highly end-use material in semi-production. Think quantities around somewhere between like 6 to 60 is usually a good range. Is something to think about if you're looking for something not quite 3D printing, but not quite injection mold tooling either. Is a really good place to go. And then we mentioned a little bit of those rules, like from my design features, look at our design guides. Let's think about the technology you want to work with. Even work with us. Our live engineering support is always available to make your project a success. And we can help guide you on which direction to go to. But it's just really, really important to say that when you are looking for end-use production with 3D printing, we really, really want you to focus on designing it for that process, because that's going to give you the best repeatability that we can offer. Because believe me, the technology is going to do the best it possibly can to replicate your 3D CAD design, but each one of these technologies has its limitations on detail size or gap resolution, for example. So if you're designing for that process in mind, then you could predict that whether I'm building 1 or 10,000, that you have that you know exactly what you're getting out of that. And again, we can help you with our design guides as well as our data sheets on what type of environment, what type of environmental performance you should expect out of these, whether it's tensile strength, impact modulus, chemical resistance. So this third task though is probably the biggest constraint when we talk to consumer products, where typically in 3D printing, parts that look good tend to not be that strong. So what Tommy was going over were this, these direct metals and these other thermoplastic printings. But if you get down to the details, you're going to find that powder kind of sugar cube finish, or if you or you'll find that layering, that kind of coarse layering from FDM. These are strong parts. They're very, very functional. But our customers are just used to what they already know, which is this machined or tooled part, which tends to have that smooth or that texture look that it's just what we're used to, right? So we're finding more and more acceptance of as-built finishes for additive manufacturing components. But depending on what type of market you're in, that's definitely a consideration. And maybe a consideration, for example, 3D printing the stuff that's inside your component, but maybe urethane casting or injection molding the stuff that's outside if you have that type of marketplace. So you can still take advantage where you can with production and just-in-time manufacturing. But definitely design life, your demand schedule. How much do you want to have on hand? How much do you need on hand, and when? These are all questions that you really need to ask yourself, and it help guide what manufacturing process will help you build into. We are really agnostic when it comes to technology here. We just want to be able to offer all the options that will best make your project successful. So always feel free to reach out, take a look at our resources, and tell us about the project. And whether it's a time constraint, a scope constraint, or a pricing constraint, we can usually find a solution for you. So again, we offer a lot, went over that, and we are constantly growing the markets that we're working in. I really like this one, the 86% of Fortune 500 medical device companies. I mean, we are really, really building strong marketplaces. We're in the top aerospace companies. We're working in tech, but you see Xometry parts everywhere, whether they're machined, they're molded, or they're 3D printed. We're there. We're in the assembly lines of major automotive companies working for jigs and fixturings. And because of the diverse technologies that we offer, we just want to be that platform for manufacturing needs, just in general, whether it's prototype to full production. And of course, we have our resources, went over design guides, went over some of our blogs that we were talking about. And if you want to be entertained and love quasi-science, definitely check out our engineering challenge videos. And there's the new one coming out, right?
Yeah, it actually went live today.
All right, so Xometry.com, scroll to the bottom of the page. There's a new video very similar to this Will It Break Me, but we have more materials that we put to the test. So that's my plug on it. But it was a really fun shoot, and it's always cool to kind of see how these materials behave in real life, right? And given under certain stresses. So we're usually, we're putting torque to them, or putting impact, or we're putting heat to these, and that's what we've really built this series around. And on our website, check out the chat bubble. Email support at Xometry.com. Everything from FAQ, like general questions, to purchase orders. That's going to be your email to go to, and our team will take care of you. And of course, you can always give us a call. So we are open from 8 a.m. to 9 p.m. Eastern time on the weekdays, and we're here to help you out. So as always, we got that digital interface. We have our live engineering support, and our goal is just a successful project for you. Oh yeah, and Shilpa, do you want to talk about the referral?
Sure. So we have an enhanced referral program that makes it really easy to share Xometry with your friends and your colleagues. So it works by sending your invite link to as many people as you like. There's no limit, and you'll give them $50 in custom parts for their first order. And then when they order, you'll receive $50 in custom parts, and that's for every successful referral. So you can find your own invite link at xometry.com/refer.
Yeah, I wish I called it Zombucks. We had such a chance there, but yeah, you'll get your referral credits, which are dollar values that you use against your orders. So oftentimes, as a refer a friend, you basically just paid for your prototypes. Also, Hunter Guerra is one of our product managers at Xometry, and we are testing out new things. In fact, you may, like, spoiler alert, but you may actually see a new design of our quote site very, very soon. And Hunter has been at the center of a lot of these efforts here. So if you all are interested in trying something and checking something out before it gets released, I know I'm personally working on some injection molding workflows too. Email Hunter, and we can go ahead and get you signed up so that we could bring you into our beta program here. And I know I talk too much, but let's squeeze what we can into the next 5 minutes for Q&A, and then I can always follow up with email as well afterwards. So
yes, let's use the last couple of minutes to devote to some questions we've gotten. The first one is, how accurate can FDM or fused deposition modeling get?
That's great. Yeah, that's a really great question. So typically we're building on two size platforms. So the smaller platform is about 14 by 16 by 16 inch cube, and the larger platform is about 24 by 36 by 36 inch cube. And so on the layer resolution, we're typically building about 10,000 layers on the smaller one and 13,000 layers on the larger. Usually you should expect that plus or minus 5,000 for a part under about 4 inches. I'm going to give a little bit of warning on anything that's like an internal gap or internal hole, just to kind of give yourself a sanity check. You may want to offset that wider by about 1/4 thou or so that hole, make it about 8 thou larger in diameter, just in case there's a little plastic burr or something that could interfere with your fit. That's usually a trick of the trade, even with SLS and DMOS, as well as opening up those thin walls or those thin gaps and holes a little bit, just in case there's a burr or a little bit of a thermal closure that happens. As the parts get larger, you're going to start to expect about 1 to 2 thou per inch deviation. So it's not necessarily that it's going to deviate that much. It just means that the predictability of what's going to happen to your design is like we have to put some kind of wiggle room in there, because think about this is your design. It's the first time on the planet it's ever been built is when we make that. So the process is very repeatable. If we built it twice, you're probably gonna get the same part twice. But how those tolerances come out on the first run, we really have to have a more broad tolerance range, because it depends on the material, it depends on your part geometry, when we're actually building that process.
All right. The next question is, any thoughts on moving to 3D printing with carbon fiber build material?
Tommy, have we got any CF requests? Yeah.
So, you know, in terms of carbon filled materials, you know, to my knowledge, that's available in SLS and also some FDM equipment. You know, in my experience, it seems to be more of a niche application in that when you start introducing carbon fibers into the material, then you get increased performance in terms of mechanical strength, but it may be somewhat to the detriment of overall feature resolution. You know, so overall, we've got partners that we could potentially look at the options for that, but as far as well, I'll also say, touching on the FDM options, like I know that Mark Forged has a platform that's coming out that introduces carbon fiber material, and one thing that I've seen with these types of materials is that you got to be very careful when you're building with those, because they could potentially warp and it may not translate well to larger parts. So I guess the short answer is that yes, I'm very aware of it, and I'm excited to potentially do more of it one day, but right now I kind of feel like the technology is going to need to mature just a little bit more before it's really commercially viable for everyone.
Yeah, and Tommy's got a point there, especially on the larger parts. So I've had some experience with CFSLS, and you can get some very crisp, lightweight pieces out of that. But the larger you get, the more risk you put into the actual overall geometry of the part. And the FDM Fortis series does have the nylon 12 CF that has come out recently. But I can even tell you, running nylon 12 on FDM, you run the same thing that you run into with nylon on SLS, which is large, broad parts tend to misbehave a little bit. That being said, I know we're running low on time, but I do want to say, if there is a custom material or a process that you're interested in that you don't see on Xometry site, I could tell you that we have a lot of manufacturing partners on our manufacturing partner network with just about every 3D printing technology that you could imagine. And if there is a special case or need, sometimes we could give you an alternative that we already offer, or we could directly source that. And under our website, you could actually select custom material as one of the material options. And we want you to put it into your notes what that material will be, and just make sure that you set in your quantities you need and press request quote. And it'll actually go to our team here at Xometry, including Tommy, and we'll make sure to get that quoted out, or at least reach out if we have any questions about that. But the reason why we had that custom field there is very similar to the beta program that I mentioned. Is we want to see what the demand is and where you guys are going, because we do have these options available to us, and it's just a question of when do we put them on our site.
All right, we have time for one last question.
Let's get one more question. Yep.
Can you say anything about pressure tightness, aka gaseous media, for DMLS metal parts?
Right, I can help with that, Greg. So I think what we're asking here is basically what level of porosity can be expected with metal parts, and will they be airtight? You know, it will be somewhat dependent on the material as far as what the bare minimums are, but I will say that DMLS parts, everyone strives to have 99% density or better on their printed parts. And you know, typically, as long as you have a wall thickness that's 1.5 millimeters or greater, that's going to be the bare minimum in the Z direction to really get that airtight seal. 2 millimeters is better, but realistically, on certain features, I have seen cases where even down to 1 millimeter or about 40 thousandths of an inch. Sorry, I'm doing the conversion in my head. That tends to be airtight on vertical sidewalls. So yes, those materials are fully dense and they're airtight.
Yeah, and to that point, like with quantity 1, that 1 millimeter may be okay, but if you're like, let's make 40 of these, I'd recommend bringing up to that 2 millimeter, because again, we want to be more conservative when we're in production to make sure that we have a very repeatable result, especially when you're talking about something that needs to be gas tight.
Yeah, that's it for questions. If you have any other questions, we'll be sending out the webinar as a recording later on, so you can reply directly to Greg.
Yeah, and we're always happy to talk about this. Again, support@xometry.com is for any general inquiries. And as well, at the beginning of this webinar, we had our email addresses available, so definitely check out the recording. But we are very excited to talk this subject. I mean, this is our passion, this is our living here. And I like to say, like, you know, between each of us, we cut our hands about 10,000 times on this product, so you don't have to. So if you do have you know, your next production goal or a project in mind where you're like, you know what, maybe I could use additive for this, please reach out. We're always happy to help. And without further ado, right? But yeah, thank you guys so much again for attending this webinar, and I look forward to speaking to you a little later. So thank you so much.